what we'll do is we still have a few more basics to cover. We'll start with line plots and univariate data analysis. These things hopefully will be quick. Because they are simple, at least some part of it will do. You'll repeat after me so that you get practice of the basics. But after that, we will move a lot faster because we have a lot of visualizations to cover. If you remember, where are we? We have done the wealth of nations only. We have all of these things yet to be done, right? So we have a pretty long day. So one request, guys, can we reduce our lunch to, well, I was thinking, somebody suggested, because most of us are remote and some of us are going home and so on and so forth, could we reduce it to half an hour? That will save us time, and we could actually try and end the day on time, especially that will be helpful, especially for people in other time zones, India, East Coast and so forth. Could we reduce our lunch break from 1.5 hours to half an hour, guys?
Make it 45 minutes.
45 minutes. Okay, how about 45 minutes, guys? Any objections to that? Anybody? It's not possible. Okay, so let's agree to have only 45 minutes lunch break. Right? Now we will do the line plots and univariates before we get there. So on we go. We changed, and by the way, this Gapminder will post it to the course in the break, in the lunch break. Let's now, so then now that you have practiced it on your own, of course, now you can have fine. We'll go to visualization, line plots using, first of all, of course, the okay. So what do we do for line plots? There is a date. This data you actually didn't post online. You have to give the URL, Kyle. You have hardwired it.
Okay. Yes, I'll do that.
You did that. So I could fix it right now. 1 second. Let me pick another visualization. Plotly bar sector the data. I don't want to type the whole location.
Yeah, it is available online. I mean,
in the support vectors, this
yes,
vector,
yes, it is available.
Let me make sure that it is indeed. Oh, sorry. Source is equal to, well, okay. And this is so this is quite a handful to type in. So I'll just paste it. First, let's see if it lands. Oh no, trackpad, because it has a plus
CSV. V is missing in the end.
Oh, that's right. CSV is missing. No, main plus. Let me just. Oh, there is a double quote here, and plus double quote. Yes. While scanning literal. So let me just put it in the same line. I don't have this. All right, let's try it. I'm sorry, starting out. Okay, it should end with a single quote. Now we are in better shape. Yes, so I'm going to paste this onto the Slack channel, and the folks can just take it because it's not reasonable to. All right, so this is data that's been curated by NASA about surface temperatures. Now, what it looks is not in absolute terms the temperature itself, but it's deviation from the norm. Right? So it takes a certain value as what you expect, and then it asks how much is the surprise, how much is the deviation from the norm, and it is looking at data from 1880 to present, which is a pretty long history of data. And we should see, obviously, these days, global warming is a universal concern, and let's see if we see any patterns in this data. remember, global warming also doesn't necessarily mean that the temperatures will keep going up. In many places, for example, there's people, we have Avanti from Minnesota, she'll testify that global warming means very, very severe winters. For example, right? Unusually severe winters, snowstorms, and so on and so forth. So it manifests itself in strange ways, and we'll see some of it. So we take this data, you see the year, you see the month. In this year, the 12 months, you see, then you see the variation, January to December, and so on and so forth, the annual things. We'll look at that. By now, we have all become good at describing the data. It is all numerical data, so we don't have to do impute is equal to all. And you can just do .t instead of transpose. So this is again good. It's synonymous with transpose. This is a sort of a NumPy notation to say .t. Then what do we do? Can we, this is data, right? Like let's say that we can see for every year these values. It would be worth plotting these lines for each year in that. Right? So this is the line plot. You can see how the data looks over all of these intervals. Right? It is just default. You take the annual change of temperature, right? Or the deviations in temperature from the norm. And what do you notice? After a certain time, these deviations are all trending to, what's the X scale here? Data, oh, just the values. So not the X scale is just the values or the deviations. So when you look at this, where do we, this, it is projecting it out and drawing it for you. And you can see that the temperatures do seem to be going up. Okay? But obviously this is not fun. Creating a line plot is as simple as one line, data jd.plot. So I will just wait here, guys. Let us do this line of plot. We are plotting one column, J to D, which is essentially the average temperatures. And we are saying, okay, let's go plot it. And we are using the default style. Are we all here, guys? Simple, two liners. Right? You set the style to basic, I mean default style. In other words, if you don't set your style, then what happens? This is how the plot works. You're looking at the column J-D, which is the average for the year. And then you're just calling it on the data dot plot. By default, it will plot a line. Can we move forward, guys? Have we all done this part? It certainly leaves a lot to be, I'll assume, and since nobody objected, assume. So then we do all the usual things we do. We apply style. So what are the things we like to do compared to this very basic? By now you're in familiar territory. We would like to resize the figure. We would like to apply a ggplot theme, good theme, apply a bit of transparency for aesthetics, add a title. The XY labels, I don't even see those. You need to improve, or if they were, you want to improve on them. Here you don't see them. Apply LaTeX formatting, it just looks nicer. And then use a tight layout and remove clutter. So here is it. You created this plot style. You put all of those aesthetic elements there. Right? Figure size 10 by 5 and so on and so forth. So now 2:1 ratio. You do that. Let's go do that and see what happens. And then here is the next element is this part, guys, we already have. I'll just copy paste it to the, it's like, or could somebody, Kate, are you copy pasting these things? Can I just?
Yeah, I'll do it.
As you, okay.
Yeah, one of you do that. One of you do that. So this is just a style element, nothing fancy. So we'll just copy paste it into your stuff.
It helps you keep awake, Kyle.
But while this is a copy paste, now let's plot it. All we do is, see guys, we are not doing something different. We're plotting the same line plot. but we are being sensitive to the aesthetics. What are we doing? We are applying this style properly. All of our parameters, RC parameters, update with this style. And we are saying it is still data.plot, but now we have added some elements. We have chosen a color and annual mean, legend, label for legend. And the color has become royal blue. Interesting, I'm seeing this royal blue for after quite some time, actually. In India, royal blue is the color of the ink we buy. I don't know, do people still buy ink in India? Anyone know?
Yes.
Right.
It's cool. Yes, we do.
Yes. This was the color of the ink I spent most of my school years with. Temperature, TSMC, temperature. And so then let's do that. And this part I would recommend that you type in. So this is word typing in. So let's type it in quickly, please. What is this doing? It is just adding to the plot. It's adding a little bit more labels and colors. Furthermore, it is also saying, do show the legends. It is setting a title and a subtitle. Do you notice that super title, or the overall title and a subtitle? Two statements. Right. Again, nothing unusual. By now, these things should have become very familiar to you. So let's type it in, please. No, would you please just type it in, this part. This is just to help you develop muscle. By the way, this internal text, you can, if you want to keep it brief, you can keep it brief and you can remove the LaTeX part. Do you need, anybody needs another minute to type it in?
Yes, please.
Kyle, I like your judicious use of both title and super title. Now we move forward. Are we all done? Albert?
Yeah, I'm getting some error, maybe invalid syntax. Maybe I typed something wrong, but you can go ahead.
No, just inspect and see which line you're getting error and try to fix it. Because this is going to develop further. So it's worth.
Oh,
What do you
I
the
missed
plots
the equal to sign. Oh, still an error.
Inspect it line by line and see where you differ.
Yeah, it's saying error is at where I have size 12.
Size is equal to 12.
Text. Yes, global temperature.
You must have forgotten the comma before.
No, I do have those as well.
Okay, this part, let me give this part in slide, just the lower part, since you're getting that part wrong. Oh. Oh, sorry. I don't know why it's showing up as so bad. Is that better? Okay.
Yeah, thank you. I will copy paste.
It's working now?
No, I have to try. Just
So once again, folks, look at this thing. It looks aesthetically, it's a vast improvement over the baseline. Anyone else? Albert, are you there?
I'm just pasting it.
Okay.
taking time, but hopefully it will work. Yeah, it worked. Thank you.
Yeah. So now what happens is you change the plot and you're looking at the temperature and you have changed the
year, yeah.
the year as the x-axis. So slight change.
So
This
early
is
on,
it.
it was plotting with the index alone.
Index, yes.
That was not very informative because we want to see the year.
That's right.
So
Yeah. So instead of having which data point it is, because it's sequentially there into the future, it's not very sure. So obviously we change it to year. It gets better. It looks like this. Right? So that is only one small change. Now what do? We do multi-series line plot. So let's first see what we are getting at. Let's get a glance at it. Right? There are seasonal temperature deviations. So these are the four things. So Kyle, what are the explanations for the symbols?
So this is DJF is December, January, February. MAM is
March,
April, May. Yes, June, July,
July,
August. Yep.
September, October. Excellent. So we are seeing the temperature variation over the years for all of these. So we have essentially grouped it by. So this is what we are going to do. How do we do that? We have these things. You look at the data. You have all the columns. Now what are we going to do? You are going to limit the data to these individual columns. This is one way. The other way we could have done it is we could have done a group.
Yes.
Groups. You could have grouped by that. In the past, we used to group by, but this is fine. So we do it. We filter the data down to specific values, right, of this, and from there, season name, and from there, all we do is we overlay multiple plots. So this part, multi-plot, I'm assuming that we are all here. We are up to here, guys. The years.
Yes, up to the line, the first one. Yeah.
So then this needs a little bit of discussion. This is very simple. You're just saying data.columns, right? And you're looking at, because she happens to know that the column she cares about, if you look at the data frame, way up here. Yeah, look at this. Here, you start with the first column year, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so you're starting from beyond 0. This would be in Bexted, starting from a 0, this would be 10. Yeah. So you're saying all columns here. What are these last 4 columns? What are their names? Right. So those names she gets now here. Saying, look at the 14th on. So you get this last 4 columns. It's just a way of extracting those columns. If you wanted, you could have just hard coded it or done whatever it is, but you just need the name of those columns, those seasons. Why would we need that? Because we want to, this is the thing, line here. We want to cycle through each of the seasons and only render one line plot for that particular season. Limit the data to that particular season and just plot that data, right? So this, in the world of those of you who do data or SQL and so forth, this would be projection, because they are projecting on the columns. They're limiting data to the columns, specific columns, right? So you take this data, now you do that, and now you're plotting it. Now, this part of the code, I think it is work, because there's not much visualization aspect, but it's about manipulating data and sorting out the 4 lines. I will just put it in a code block, which I hope, code block. Let's try our best here. Yes. So
I can paste it. I can paste it to Slack. Yeah.
Okay, if you could. So let's run this code block so that we come to this multi-line thing. So whenever you overlay a lot of lines, remember to play with the transparencies. Right? If you don't play with the transparency, those lines will all start becoming hard to decipher, hard to tell them apart. Seasons definition is right there in the code, Sanjeev. Do you see this line of code? Columns, right? You just pick the 15th column onwards. 14 means beyond, start with the 14, but indexing from 0, which is the 15th column onwards. One distinction, guys, all these languages, Java, C, C++, Python, they start counting from 0. Like it's a unusual thing. Then languages like Fortran starts from 1, and Julia starts from 1. So when you do Julia coding, I don't know if you do that. If you have an audience, I would love to do ML100 using Julia. You'll see a different form of indexing. So now, guys, are we here? Sanjeev, are you able to reach this line? Okay, wonderful. So let's move forward. Then you you look at something else. You have changed the temperature, and we are looking at it at the granularity of the year. How does it vary by year? Right. The seasonal temperatures, how are they varying by year? Now here is
by decade. So
by decade, sorry, 10 years. Group, I mean, sort of at the 10-year interval, but more coarse-grained view of this thing. Okay. So you're seeing the seasonal temperature, far less granular. This is it. The trends are more obvious. Generally, what happens is that data, sometimes more data is less informative. It takes a bit of effort to see that it's rising. It is visible, but sometimes taking averages over this, and here it is values taken over decades. And later on, we will learn, or if I give it as an exercise for you to do, that you can look at something called moving averages. Right? For example, when data is very fast fluctuating, you can look at moving averages. Maybe we can keep it for one of the sessions this week, how to render data as moving averages. So anyway, this is data as is per decade. So the code for this is,
yeah, I posted it on Slack.
yeah, season. You just go by 10. Nothing more. This is just a data manipulation. The crucial line is this: group by decades. Right? And then plot it accordingly. And then take the mean per decade. So this is, those of you who do, for example, Spark or anything SQL, you would be very familiar with this. This is literally aggregate by, and so on and so forth. So far we are here. Are we all here, guys?
Yeah.
Next, let's go to the area plot. One of the popular visualizations that sometimes helps people get a sense of what's happening compared to the norm, because we are looking at temperature deviations. Deviations can be positive and negative. And often we get a much more sort of a visceral sense of it. When you spill a bit more ink, you make it into an area plot. So this is the area plot. Look at this. The x-axis is the year, y-axis is the average annual deviation for that year. What is the deviation from the norm for that particular year? This is royal blue. There is no need for stacking here. It is there. And the rest of it is exactly the same, the title and this. So let's color blue, etc. So this line of code, guys, can I expect that you can do it on your own? This is easy, isn't it?
Yeah.
It is a minor variation of what you have. So what I will do is, because there's no new learning here, I'll assume that you can do it and we'll give you the code. Notice that because you use LaTeX and the mathematical notation, it was much easier to write decreasing. If you notice on the y-axis, LaTeX has very sort of excellent formatting for scientific notations and scientific symbols and math and so forth. So we go there. Next, we can also use vertical lines as an alternative to area plots for a sharper look. So we draw the vertical lines for each year, starting from 0 to the annual temperature deviations. So this is it. This is just a variant of the previous one. What you do is, instead of area, you say here, what did you say? If you look at it, the method that you use is area. But you could use V-lines. Now, V-lines is not directly built into Pandas plot yet. So you have to use Matplotlib directly for that, which is here. And when you do that, again, a minor variation, nothing unusual here. So this code also will just give it to you. So you just paste it in your notebook and see if you can draw out the V-lines. The only crucial difference is this particular line. So X is data, Y minimum is when you show that NP0 is data, so the shape, whatever it is, and Y max, how many data points you have. You have given your min max, and you're just going ahead plotting this data. All right, let's move forward. Now we can customize. So now what do we do? Let's go and look at the result. Do you notice that when you make a plot like this, it's a little, all that you see is a lot of ink on the page. Maybe we can use color as a way, as a means to convey what is happening. And now in our minds, we always associate, let's say, a blue with cold, icy, and red with hot. So what if you color this by the value, whatever the temperature value is? Negative is blue and positive is red. And this is, again, what is this? This is a use of a color map. You notice that? And so what you do is you take the values, data minus this, you take the range of the data. What is the range of the data? And then what you do is you use a color, you create a color map, cool to warm, which is perfect for temperatures. And you divide it into that, the values into that, so that all we do is this particular thing. This thing is the main change. You give it a color map, and you make the lines a little bit bolder. Line width is equal to 3, will make it bolder. This looks a bit too pencil thin. You make it a little bit bolder. And when you do that, everything else remaining the same, you will get this. Right? And it conveys how temperatures have been changing over the years. Clearly, our temperatures were going down, and then suddenly, when did the automobiles come? When did Ford start making those cars? Somewhere around the
1900s.
Anyone remembers?
Early 1900s is when the Automotive.
2019.
Automobile.
Yes, somewhere around this. Do you notice something interesting? Well, maybe may not be the only reason. But after that, coincidentally, you see that the deviations are not heading towards the positive territory. Right? They're shrinking from the negative, and they are gradually making their way towards positive territory. Now, there are many reasons to it. It's also coincides with heavy industrialization, infrastructure buildup, and so on and so forth. But there are many reasons that could be there. And then a lot of people could argue, for example, that this is the natural rhythm of the earth, right? And so forth. So whatever reason, this is a reality. And this is all about line plots. Was that simple? Kyle, where's the strip plot? Did you check in the strip plot?
I haven't checked it in. I think I'll share my screen.
Yeah, would you like to finish this
Yeah.
discussion with the strip plot?
Yeah.
And check it in then.
Yes.
I love it.
So now we can just visualize this whole plot maybe just with colors instead of using heights.
Yeah.
So we use V lines and we set them to a constant height. And we use the same colors we used previously. And once we do that, we get the strip plot, which is, you might have seen this pretty famously everywhere after the COP26 summit. So this is quite famous from that. So
Isn't
can
this
create
the
it.
main mask? I mean, the main visualization for that conference, the strip plot, COP26.
Yeah.
If you just do
A question,
COP26,
Asif.
come again.
There's a small question here. So I think we can also make animation with this thing also, right? Moving from
yes.
left to right,
Of course.
moving from left to right, and then probably can we do annotations during that movie or specific points? Hey, this is the point at which we started, forward
Yes, yes.
started, or something like that.
Absolutely, absolutely. Those are fun projects. Please do it. You realize that you have all the tools to do that now, right? You can keep annotating it in your visualization and your animation, putting landmarks there, saying
Yeah.
every bar that you put that is significant, you can say, this is what was happening at the time.
I think that's the
Yes.
connection to the data to the underlying reality, basically.
Exactly. You're mapping it to world events.
So this cool warm is a method.
Cool warm is a color map, one of the color palettes, standard color palettes. See, you should look at the color palettes. Well, so it is. Do you see this, guys? Okay, it will come to sequence. So you'll get cool warm here. Divergent. Let's go down.
Yeah, diverging. It comes under diverging.
It's perfect because our human mind, through all the colors that have been used, we associate blue with cold, red with hot. So this is a perfect color map to pick.
That's good that you showed that. Otherwise, it's like, how do we get that?
Yeah. No, these color maps that are there, again, I'll repeat this thing, guys. Color maps have been created with great thinking and research and so forth. And people spend endless time creating good color maps. Their entire papers and presentations and curators and so forth. Use color maps where possible. Don't arbitrarily pick your colors. Because if you arbitrarily pick your colors, quite likely you'll get it wrong. Some sector, like for example, colorblind people won't be able to see your colors, or it will not look sufficiently distinguished, or something or the other. There's a high potential to go wrong. So you should do that.
And we can choose diverging colors.
Yes. All right, let's get back to the video. So guys, this is about the just the line. Do you realize that line plot itself has,
As in our case where there is a significant midpoint to our data. So
Kyle, you're breaking out. We can't hear you.
yeah, my internet is poor.
Yeah, it's all right. Could you please check this in, because I would like to upload this part also.
Yes.
Check this in. All right, guys. So we did line plots. Let's go to the next visualization, which I'll take over. and do after line plot, we could, so guys, was this fun? Like, are you getting a sense now? It's getting easier, hopefully. We can do the line plots in Altair, in Seaborn, and it gets better and better. Let's say that you do it in just for the sake of completeness. It is done now using this particular one is the same data. By the way, you'll have to make changes to this. Akai, could you please change this line
Yes.
everywhere? And
Yes.
the rest of the code is the same. You start, this is the Seaborn plot. Basic looks terrible. Once you apply the dash of style, it begins to look better. Nothing new is contributed. If you look at it, except for the word line plot and minor cosmetic changes, it is essentially like Matplotlib. Then you improve upon it. It again more or less stays similar to what Matplotlib produced, not a vast difference. Then you can group the data. This is basically the syntax, and you can look at the annual. Again, if you notice, much of the code is the same. The only difference is instead of plot, you're using line plot explicitly. Yeah. SNS, not that much value. So because it's not adding too much, this notebook sort of ends here. Let's look at the same line plot now using Altair. So when you do with Altair, what happens is that this is the explanation of the data. We'll go, a basic plot is, we don't have a, okay, trust it.
Okay.
Right. So you notice that a very basic Altair plot is, by now you realize that there's nothing. The only difference from bubbles to lines is this word. You see, instead of marking it as circle, you're marking it as line. In the language of graphics, grammar of graphics, you would say that this is the aesthetics you picked, right? This language is, of course, very typical of Altair because Altair itself, coming ultimately through Vegas and through D3, has the grammar of graphics thinking built into it. So this is it. It looks better. We can move forward and we'll give, so we won't do it right here because there's nothing new here except for this one line change, mark line, and some minor cosmetic changes. So then we improve the legends, the title, and so forth. We do multi-series. Here, we need to understand a concept called transform fold. Right, sorry. And what it does at this moment, it gets complicated because it has to do like with this changing the shape of the data and so forth. But anyway, here we go. You change it to be about these things, these four things. It's an Altair thing. It begins to look like this. Again, looks pretty good. Then how do you do it by decades? You do it like this. And how do you do area plots? Nothing. So you guys notice that none of this is, other than the transform fold, which you should become familiar with. Nothing else is new. It's just marked lines. Everything else you're familiar with. Area plot, you can make it into area plot. And okay, let's go finish it. You know, make it at parity with Matplotlib. This one.
Okay.
The lines and the stripes. Bring lines and stripes.
Okay.
Seaborn is not needed because you'll essentially use the same syntax. But here we should do that in finishes. Please.
Okay.
At this moment, commit whatever you have, but eventually do that and we'll upload it to the website with the updates.
Yeah, sure.
So that is that for the line plots, guys. We have about 20 minutes to the lunch. What I would like to do in this 20 minutes is I would like to talk about something, another visual, it's another set of univariate statistics things like box and whisker plots and violent plots and so forth. So we will take the same auto data set that we have been using for so long. By now, you're all familiar with the auto data set, right? Mileage, how does mileage respond to weight of the car, the number of cylinders, the horsepower, and so on and so forth. Right? These are the things. Mileage is, think of it as your target variable. It responds It varies in response to the number of cylinders you have, the displacement, the size of the engine, the horsepower, the weight of the car, etc., etc. Right? So these are all parameters that affect, and mileage, of course, improves with years. Yeah, by now you're very familiar with this data set, so I won't. Let's not go over this data set too much. So univariate statistics, the basic thing you can do is draw a histogram. What is a histogram? Histogram has, what it does is, if some feature like here is MPG, miles per gallon. Miles per gallon, you would agree, is a continuous value. It's a number, but you discretize it, you bin it. You say that, hey, you know what, values that are between this and this, from here to here, whatever that is. Let's say from 8 to 12 is this, from the next to this is this. You can specify what your bins are, number of bins. And then you take, you count how many in the data, how many data points fall into this bin versus the next bin and the next. So your y-axis is the count, right, or the frequency. How many data points fell into that bin? What does it give you? It gives you a sense of, what does it give you a sense of? Where is the data more concentrated? So we can clearly see that in those times, most cars gave mileage in this zone, right? Between about 10, 12, between, or let's say 14 to about 14 to 20 was rather common for cars to have. They had a lot of data, and it was fairly common all the way till about 30, I would say. After that, it's rapidly decreasing. There was some car or a couple of cars, it's not very clear what those values are, which even gave 45 miles a gallon. Right? So must be tiny little cars in those days. But it was doing. So histogram is essentially a count plot. Right? By first converting it into the x-axis or the actual feature, by discretizing the feature effectively into small ranges of bins, range of values. Now to this, let's apply a dash of style, the same things that we have been by now used to doing. I hope you don't need to see all of this. This is all the same thing. Again, what is the method we use? Hist. That's it. Just hist. Hist will draw the histogram. So could we please do this little bit? Please humor me before we break out for lunch. I will give you this particular code because this is a bit tedious. Could Kyle, maybe you can paste this code?
Yes, I'll do it. Yeah.
Let's do that. And then you can do the describe and so forth, which by now you should be familiar with. Write this line of code. Actually write it so that you can draw the histogram. Are we all able to do this, guys? The histogram code? Oh, have you pasted it, Kyle, yet? I don't see it yet. Maybe she lost
Yes,
it.
no, for some reason, that notebook is not opening in my.
Okay, that's all right. I
Would
will
you like me
paste.
to do it?
Yeah.
I'm
I'm
still
pasting.
available. Okay.
Yeah. There you go, guys. I pasted it. And maybe Kate or RNA, please help me out.
Sure.
So let's load this data. And once you load this data, I want you to type this line after me. Type this. So you have a histogram. This is your minimal histogram. Now you know the journey we are going to take. We're going to improve upon it. This is not extremely informative. We are going to make it tell the story properly. Right? So what does data MPG do? It just picks the column called MPG in the data. And then you call plot list. You could have also said plot function kind is equal to hist inside it, but this is perhaps a bit more intuitive. Are we all there, guys? Can I move forward? Okay. So we do this, we get this basic vanilla thing, we improve upon it. The improvements are exactly what we did before. Let's add this style element, we can copy paste it. But then the rest of it, guys, you notice that you're all familiar with this, updating the style, ggplot, and then the crucial lines are here. What do? We set the color, we set the edge color, we set the line width of the edges. These are adding aesthetics to the picture, changing the size of the picture, we're giving it a title, we're doing a tight layout. All of these by now you're very familiar with, so we'll just copy, give you the code. You can just take it. Or would you like to type it in? No? Okay, we are due for lunch, so I'll keep it like that. But do you realize, guys, that just being a little bit careful creates a vast difference in the picture, in the plot? Would you agree that this already looks like a vast difference over this? So it gets better. Then the system has arbitrarily picked the number of bins. Suppose you wanted to pick your own number of bins, say 20, and you can do that. You can specify the bin, no other change. You now have a histogram in which you have specified the bins, right? And one of the things you could do is, this is frequency, right? If you ask this question, and this is a notebook we will do. See, when you, let's say that birds are there. Okay, we'll do that in a little bit. How likely is it to see the value 15? What would you do? You would take, or in the 15th bin, the bin that contains 15, you would say, count the number as a numerator. You would take whatever the number count is there for 15th bin, and then, or the bin with 15, and then you would divide it by the total, right? The total amount of data. So that would be the likelihood of data falling into that bin. Does that make sense? Right? So let's say that you have 100 data points, and in this particular bin, 8 of them fell. So what is the likelihood that data, any random piece of data will fall here?
8%.
8%. That's exactly it. So what you can do is you can divide it by the total, and Matplotlib gives you that ability. It will do it automatically. All you have to do is say density is equal to true. Right? And then it becomes probability. Actually, we should say probability density, but density.
But the shape should be the same.
It is the same. Look at it. It's exactly the same. Look at this shape, right? And because all you have done is scale it. Only the y-axis has changed. It's become probabilities, densities, rather than counts. The y-axis has changed. Does that make sense? And so your y label should say that accordingly.
So what you're saying is the sigma of all of that would be like 100% or 1.
Exactly. Wow. Yeah. So the formal way to say is that the area under the density curve, probability density curve, is 1. If you integrate it, or in the case of discrete values, what you say is, so what happens is that each of these values, when you have discrete, statisticians tend to use a language called probability mass. Right? What is the probability mass? They all have to add up to 1 anyway. Right? So I tend not to distinguish it too much between probability density and mass. I call all of them probability density, which is very common. Most people nowadays just say probability density, even though there are some nuances. If you want to be ultra careful, you want to say a mass function, probability mass function. Right? But it is that.
So what you're saying is that people who are looking at data,
Yeah.
they tend to look more at the shape and things like that, and not much at the actual
Count.
value of it.
Actual
They have mentally like done that. They
Yeah.
can always go back to the
Back and look at it.
But
Exactly.
most of the time they just look at this, I don't know, scale of
The density
0 to 1.
function. And why is it that we prefer looking at the density function? Hold that thought in your mind. We literally have another Jupyter notebook dealing with why density functions are gold. We'll come to that.
So another question for you is, say suppose this is very sensitive data. I
Yeah.
don't want to tell somebody what I'm showing. I want to like have some statistician or somebody concerned.
Yeah.
Then I would just show the shape to him and say that give me your interpretation.
Exactly. You would show the shape. You wouldn't keep the value. So for example, if it is dollar value of revenue,
Right.
you wouldn't show that. You would just say, okay, this is how the revenue is varying across the months. And could you help me understand or something like that?
Something like that. Right? Oh.
So now, suppose you group by, one of the common things you do is you group it by, see, a categorical. One of the categoricals here in the auto data set is, which country is the automobile? What is the country of origin of the automobile? Is it a Japanese car, a European car, or an American car? Right? That's what those origins are, by the way, America, Japan, and Europe. Okay? So you could actually group the data. This is again basic pandas. You can group the data by origin, and then for each origin, what would you do? You would plot a separate histogram. You could plot a separate histogram, and lo and behold, here you have 3 separate histograms, one after the other. You have plotted it out. And you can clearly see that if you're in origin 1, you tend to have fairly low mileage. If you tend to be in origin 3, you tend to be fairly high mileage. So if you had to guess between Americas, Europe, and Japan, what does origin 3 look like?
Japan.
Japanese.
America.
No, Japanese. They tend to have higher
Sorry,
mileage.
Japanese.
Right? So this is it. This is how you get intuition. But we'll have a lot more to say about histograms after lunch. Now let's refine this figure and let's see what are we shooting for. We are giving it 3 different colors. Can we do that? Yes, we can do that. All we have to do is pretty much add set of little bit more customizations. And here is the color palette we use based on the index. Right? Color palette is using tab 9. By the way, a tab 10 is short form of the colors that Tableau tends to use. Tableau is a data visualization dashboarding tool in which you don't have to write much code. You drag and drop and it comes about. So think of it like Excel. In Excel, you don't write code, you just drag. The UI helps you write some code. Those frameworks exist. And they are good for people who are not into programming or data science very seriously because they give you rapid ability to rapidly create some plots and dashboards. But of course, you are at a slightly, you are in a different game. Okay. So this is it. Give it an index. And there we go. A plot, subplot, which particular plot you're doing, index +1. Why? Because, yeah. By the way, this subplot, you remember, number of rows, number of columns, and then what is the index of your particular plot. So if you are making 3 plots, remember indexing, and this is where you have to remember, Pandas starts indexing of arrays at 0, but Matplotlib and the graphics community starts indexing at 1, which explains why you're adding up +1 to the index, right? That's all it is. Then you set some limits and so on and so forth, and transparencies, and you put some label, and all of it is very well explained in this in the comments here. Set the transparency. So you realize that this is all good, fairly straightforward work. Nothing, no magic here, except that it is the use of subplots. So, which I believe here also is 1 second. Right? Subplots, the same thing, subplots, 3 subplots. So you do that, now you get your color also. Now you say, this looks beautiful. Personally, I find that this is very informative. Then you say, all right, there's another kind of visualization. Do you remember the stack bar chart? So this is just a recap of it. Redo this, but you stack it, one on top of the other. Right? This code by now should feel very familiar to you. The only thing is there's a different color palette used. And so we go. So this is for the histogram, which is essentially a form of bar chart.
So can you put it back? So what does it mean over here? That origin and then the frequency.
That is right. So if you look at this, for example, how many cars are giving you 15 miles a gallon? It turns out that these low mileage, so look at the low mileage cars, 10 miles a gallon, around 10 miles a gallon. That dubious distinction goes to 1. cars in the Americas, right? Then if you look, for example, at this other end, this green, that distinction goes to, well, it's a Japanese car. But now look at something in between. What you're saying is, if you look at cars that are giving you around 30 miles a gallon, this particular one, they're equally distributed, more or less, the sizes look the same, right? When you compare their sizes, they look the same in all three regions.
So if I had revenue, right?
Yeah.
And I was trying to compare the revenue across the different regions and things like that.
Yes.
In that case, if you take the absolute values of it, some of it will just shrink away, right? If it is like a gold region.
That is right. So
So
what?
then how do you figure out?
Remember, we did
that?
proportional
Right.
bars. Use proportional bars. Proportional bar charts, because then you can compare the so for example, I can say that the revenue from Japan, let's say that I have my software selling in 3 regions, right? I could say that my Japanese revenue, Japan answers for 80% of the revenue, Europe accounts for 20% of the revenue, and let's say US accounts for the remaining, I mean, not 20, and so, I mean, 10%, it adds up to whatever it is. So linear, you can see the comparison. Now, when this happens, people sometimes say, you know what, let's use pie chart. Traditionally, people use a pie chart, right? Because all these libraries give pie chart. The problem with pie chart is, so pie chart has become tremendously debated these days, right? Because it violates the ink to data ratio, data ink ratio. Too much ink is spilled, number one, to show the sector. And all you're seeing is the arc widths and area widths, right? Now, the other thing is human eye as a perceptual sensor, a perceptual device. It handles linear comparisons much better than it handles area comparisons, right? Area comparisons always sort of exaggerate the data, tends to, right? Unless you are careful to take the square roots and so on and so forth. And most people are not, right? So that's the main problem. That's the main problem with pie chart. So there has been a huge thing that, for example, I don't usually allow pie chart. Rarely, sometimes it does make sense, but then what we use is not the pie chart, but the donut chart, in which we just show enough of the circle, fat circle, but not the inside of it. Right? Because you're just wasting ink. It's not, you don't let it become an area. You let it just wrap around and be a circle. It's almost like the bar has gone into polar coordinates, right? Which is good. But pie charts, I'm personally not a big fan. And it's not me. There's a tremendous amount of debate and scholarship on this topic. It's surprising how much it has been talked about. Right? So you find pie charts fairly ubiquitous, especially in corporate world, right? It's the instinct of people to just talk pie chart. And you can't help smiling, because hopefully if you go from support vectors in training, you will absolutely eschew pie charts and use it sparingly. There are a few good use cases to use it, but generally not much. Pie charts are, for example, good when you want to show, let's say that you're putting things into your shopping basket. So that would be 100%. How much have you filled, or how much revenue compared to the target you have achieved? Then you can show circle with that part highlighted, the gray circle in that part highlighted. Even there, people would argue that why can't you just show linear? Because then it would say you're at 80% compared to 100%. So a lot of thinking out there, and but I think that it has a place. It's not that it's completely useless. It does have a place. It does work, but use it sparingly. That's the thing. All right. So now comes the box and whisker plots. What are box and whisker plots? So let's look at the definition of what a box and whisker is. See, in the box and whisker, there's a box here, right? So you first divide the data into quantiles. The first third of the data, the first half of the data, the first 3/4 of the data, and then the whole of the data. And typically, the box represents the central quantiles, the middle quantiles, right? The reason for that is data often has outliers. You know, the last quantile will spill over and go far. So there is a formula that is used, and I'll remember that. This was, I think the initial was done by the statistician who formalized it was Tukey. Tukey created the definition of outliers. The oldest definition of outliers is, and then when, see, this is the limits of what you consider the boundaries of the outer outliers. Yeah? There is a whole definition of inner outliers and outer outliers, real outliers, hard outliers, soft outliers, hard outliers. These are the things. And then anything beyond this fence is now you circle it out to stand out. This is really an outlier. Right? So what it means is there is a car that's giving you really high mileage compared to most cars which are giving you, what is this value? The average value here, 23 or something like that. So there is a car that's giving you very high value. Right? You can do that. So this is your box and whiskers. These things are called the whiskers. If you think of how many of you own cats? Right? So you know what whiskers are, isn't it? Yes.
What's the height? The box height.
The box height is the from the upper whisker to the lower whiskers. You know the outer fences of outlier, right?
Is it like 3 sigma?
Come again? Is it?
The 3 sigma? The top one?
It is the Tukey's definition. It is. I think it is. Outer one is 3 sigma. That's how it is. Look it up. I don't want to see. This is very elementary fact. I can't believe that it's not on my fingertips. But just look up Tukey's definition or box and whisker plot definition. You'll see what it is. I don't want to be off because sometimes people pad it a little bit. You said this plus this percentage or 1.5 times the interquartile range. So for example, this interquartile range, 1.5 times this, that. People have a bit of it. And it's, at this moment, it's off.
Yep, you are right. It is 1.5. I just
1.5 times the interquartile.
Yep.
Isn't it?
Yeah.
So 1.5 times the interquartile will give you the outer whiskers. So that's how you create the limits, but there will be data that will fall outside, and that outside part is, of course, your real outliers. And now you're saying, okay, no excuses. This is certainly an outlier. No debate about it. Right? So now you can customize it, make it look better once again. So this is a bit, of course, I won't make you do it right now, but you can read it. You can color the whiskers, you can color the box, you can do that. Why would I do that? Why would I do that? Because it makes, for example, look at this. Would you agree that this really makes the outlier stand out? Isn't it? By putting it like that, it makes it stand out. You're making the box a particular color, you're showing the average in a certain way. It's good. Now, notice that the average is not in the center of the box because median and mean need not agree. In fact, they don't usually. Now, just to point this out, you could add a little notch. This highlights. What has this done? It has just made you pay attention to the mean. Yes, right. And right. So now, and so forth. You could keep going. No, actually, it's the median. It's the median. Sorry, it makes you pay attention to the median. And now you can keep going and adding a little bit more aesthetics. This also makes it a little bit better, isn't it? Fills it in with color, makes the box stand out. Then you could group it by the origin, like where is this coming from? Here are the origins of the three automobiles are grouped by origin. What do you see? When it comes to mileage, the biggest outliers are coming from, the highest outlier was coming from, like Japan, right? From Japan. Like, for example, if you worry, where is this guy coming from? Which region is it coming from? And now it is clear it was coming from Japan. 3. You could do further customizations. We won't go. You could color it. Like, for example, this is monotonous. These are all 3. Why not make them stand out in different colors? So you make them stand out in different colors. Right? And now we stop with box plot. Right? Now you see that simple box plot has gone through an evolution. It's become more informative rather than doing just like this. Right? You have evolved it to this, right? And these are the median values. You have evolved it to this level. Would you agree that this is far more informative?
Yes, and pleasant to look at.
Then there is another plot which is called the violin plot. It deals with something called a kernel density estimator. I will explain it to you, but it basically hypothesizes how or where data is more prevalent. So this is the violin plot. Obviously, if you look at it, you imagine a violin. There is a vague analogy or similarity to a violin, isn't it? So this shows you the density, the probability density, basically, or the yeah, it's just been symmetrically flipped. So in other words, so when you look at this, you may argue that there is sort of too much ink wasted. Half of the violin would have been good enough, isn't it? It's basically your histogram smoothed out and flipped. And the topic is kernel density estimates. We'll come to that right after lunch, and it's getting over time for lunch, so I'm rushing ahead. So on this horizontal, so you could build it violin horizontally. Right? So there you go. You can even render your quantiles, extremas, and so on and so forth. You can give all of those ranges type and so forth. So this is it. I will let you read this because we are over lunchtime. You could do further benefits to this violin. Now you're trying to impose the information of your box and whisker plot. You see that? Box and whisker plot information. Your box and whisker is back. If you can notice it. Right. So you can again group it by subject. So this is violin with the box and whisker plot, which is quite useful actually. Okay. Now, this thing, how did this smooth thing come out of a histogram? We will study that. It's a good topic. We'll study that after lunch when we deal with this important topic of kernel density estimators. It turns out that histograms are good, but there is something better. Histograms have a lot of limitations. There is something better when it comes to getting a gut sense of how the data is distributed. And we'll do that after lunch. So guys, at this particular